One of the steps that we took in the derivation of the speed of light showed that minus dB dx equals mu naught E naught dE dt, and we worked out both of these derivatives, which were both cos functions. When we cancel out all the common terms, we end up with the equation that the maximum E field, E naught, divided by the maximum B field, B naught, is c, the speed of light, which is a large number. This might make you think that the electric field part is a lot bigger than the magnetic field part, but it all comes down to units, and it turns out, as you'll see later, that the energy in an electromagnetic wave is actually evenly divided between the electric and the magnetic fields. So, from all of the calculations we've done, we find that electromagnetic waves look like this. If the wave is traveling in the x direction, which we call the direction of propagation of the wave, then the electric and magnetic fields are in the y and z directions. Waves where the electric and magnetic fields are restricted to being parallel to the y and z axes are called linearly polarized waves. So we assume that the magnitudes of the electric and magnetic fields of the waves we're going to be looking at only depend on their position along the x-axis. And we call this a plane wave. So if you look at the diagram at the bottom right, you can see that it's showing the electric field component, which is changing as you move along the x-axis, but it isn't changing as you move in the minus z direction away from the x-axis. And we assume that the electric field is the same on the other side of the x-axis and below it, so it's propagating along as a plane. And also what that diagram is not showing, that there is the same magnetic field component. It's at right angles. It also is a plane. Now, to have a little look at what it looks like, you can see quite a good animation there. You can see that both the electric and magnetic fields are changing in time, that the electric field is ranging from a maximum vertically upwards to a maximum vertically downwards, as the magnetic field changes from a forward maximum to a backward maximum. And you can see that the wavelength there is always able to go from one peak of the wave to the following peak, or in fact from any point on the wave to a point exactly one cycle further back. Now we know that we can draw rays to show the direction of travel of a wave, and that wave fronts are lines or surfaces that join points of equal phase, which means points on the wave that left the source at the same time. The wave fronts are always perpendicular to the rays. So light from a point source, like you can see on the left, will have rays that radiate out from it and spherical wave fronts. But you can see that as you get further away from the source, the wave fronts become less curved. And a very long way away from a point source, the wave fronts eventually become planes rather than segments of a sphere, and the rays are parallel. So, for example, the sun is a point source and rays come out from it in all directions, but we are so far away that we can take the sun's rays that reach us as being parallel. Because the electric field and magnetic field are both perpendicular to the direction of propagation, electromagnetic waves are transverse waves. We take the wavelength as the distance between one maximum and the next of one or other of the fields. Then the frequency can be found using the equation that C equals F times lambda. Electromagnetic waves show many types of wave behavior that we will examine more closely later on. They obey the laws of reflection and refraction, and they superimpose to create interference patterns. The other thing about them is that since electric and magnetic fields can exist even if there aren't any atoms present, electromagnetic waves are the only type of wave that can travel through a vacuum. This idea was so alien to scientists at the time that they came up with the idea of a luminiferous ether, or light-bearing ether, which was, they thought, a transparent medium that filled the whole universe and provided the medium for light to travel through. Even though the Michelson-Morley experiment failed to show evidence for the ether, the idea persisted until Einstein's theory of special relativity showed that the ether idea was not needed.